All right. I'm not so patient on Zoom. I just want to get started, but I do know that sometimes people come in a little bit late. So if you haven't done it already, I would really appreciate you putting your name and email address in the chat bar, because some of you guys I don't have contact information for yet. And we send out a nice little certificate to thank you for showing up. And if you do need CTLEs, let me know that. Let me know that you need it in the chat bar. If you have signed up through Frontline, I will just put the CTLEs through that way. If you need CTLEs and you have not signed up through Frontline, then I will need to send you a paper copy, and I will need to connect with you. Oh, Gary, I connected with you earlier. Good to see you. I'm glad you could make it. And Deborah, I'm glad to have you on board. It looks like nobody else has chimed in for a little bit, so we might as well get started. Before we get started, I wanted to let you know of a couple of other programs that we have coming up. We will have a program called Sensory Tools for the Classroom. We have an occupational therapist that will be putting together a sensory baskets that you can borrow from the Teacher Center. And her presentation will be how to utilize these things in the classroom. Lots of times kids have behavioral problems because they really have sensory needs. And that will be on June 10th at 3:30. And then I'm really excited to have Elizabeth Hambelt at 3:30 on June 15th. And she will be doing a presentation on the transition from high school to college for students with disabilities. There's just a tremendous amount that I did not realize. And the law changes, and there's a big difference between K-12 and 12-16. So she'll come and present on that, and we will have several copies of her book as well. And so we are really happy today, or excited to have the authors of this book, 3D Printing, by Stephanie Torta and Johnathan Torta, and you guys can take it away.
All right.
All right. Well, thank you, everyone. As he said, I'm Stephanie Torta, and the one over there is Johnathan Torta. Unfortunately, my webcam is not very good, so I don't have my video on, so I do apologize for that. But yeah, let's just get started here. Just a couple of quick things. It's like if you have like a quick, short clarifying question during the presentation, feel free to go ahead and ask that. If you have a longer question and more in depth, we do have a couple of Q&A sessions already kind of built in. So if it's a longer question, feel free to ask during the Q&A for more in-depth information. Anything else, John, before we begin?
No, that's looks. Can everyone hear me all right? Cool. I'll get the share going. There we are. And that, of course, now moves everything on my screen. So if you give me 1 second here.
The joys of Zoom.
Yeah. Well, it puts everyone on a single bar.
So while he's doing that, I'm just going to go over kind of what we're going to be doing, and it's going to be kind of like an overview, and then we're going to go into a little bit of depth with the type of printer that you guys have, yep. And some of the things that are going to be in our book, and we're kind of going to go through it. We ordered a number of different books, and so you're able to just go through there and go into a little bit more information. So anything that we don't cover in this presentation, chances are you're going to find it in the book, and you can always ask us if you have any additional questions afterwards. Some of the cool things about 3D printing is chances are you either have it in your life and didn't know it, or you didn't know it could do all the stuff that it can do. It's pretty fascinating. So, yeah.
All right, so everyone can see the share all nice? Is that readable? All right.
Yeah, it's legible.
Cool. Yeah, we've already gone over a bit this.
Well, yeah, those are us.
All right.
I'll just give you a little bit of my background. I'm actually a graphic designer and multimedia developer, photographer, designer, basically a creative. And I graduated from Edinburgh University and then Emerson College, and kind of worked at both of them, teaching as well. And well, BU and Emerson. And basically got into I don't know, authorship. Well, first my storyboard book, which is the one I'm holding there. And then I teamed up with John to write the 3D printing book, because he's the 3D printing guru. John, you want to introduce yourself?
Okay, so yeah, my background is I've always been playing with a wide range of things, from anywhere from computers to electronics. And I was on the bottom floor when DIY 3D printers came out, and I built my own. In fact, in a later photograph, you'll be able to actually see the wooden 3D printer that I built. Actually, currently, I'm handing off a 3/4 scale printout of Dr. T, a sports star, that is going to be picked up momentarily to be brought to a studio, molded, and then bronzed into a statue. So yeah, it's 3D printing is now part of just about everything. It's an alternative method of manufacturing.
Just a slide on our book.
Yep.
It just outlines it. You don't have to read it now, but we can, of course, share the deck with you. But it's just basically what the book covers. And basically, I think, at least on my end, it covers from the beginning until all the way at the end of the finishing. It is a beginner level book. It's not intermediate or advanced, though I do have some intermediate like steps and projects in it. We are writing a more advanced, intermediate and advanced book that's hopefully going to come out next year. But this kind of covers up what the book is and kind of what we cover inside of it.
Yeah, because this book is effectively an intro, but also it covers how do you utilize a 3D printer and how you use it. One of the big things that a lot of the books miss is how do you maintain it, how you clean it, how you calibrate it is one of the largest ones, and what do the various materials will either do to your printer, or you have to have specific printers for. So, all right, so let's move along here. Okay, so 3D printing pretty much starts as additive manufacturing. We have here formative is what you would normally think of like molds or casting. You'd be pouring a molten material into a mold and breaking it out, and you would have a finished project. Subtractive would normally be carving, CNC machine, and that would be taking a block of material and removing material until you have your object. Additive is the exact opposite of subtractive. You'll be building up the material until you have your final project, your final object. And this actually has, you'd think it'd be very similar to subtractive, but in like with formative, molds have to be made in a very specific way, or you can't release the mold. You can have areas which you can't get to, the flow of the material into it. Subtractive, even with the higher end CNCs, there are spaces that the CNC can't get into. So like an engine block still has to be made in multiple pieces and put together with gaskets and bolts to finish the engine. With additive, things are a little bit different because you're building it from the ground up. Intricate internal spaces can actually be built. So let me go to the next one. And here is we'll be coming back to this. a pretty big list of all the different current 3D printing technologies. You don't have to look too closely at this, but I'll go over the highlights because we'll come back to this. Anywhere from laminating sheets together, almost like plywood, and then cutting them out, using 2 different types of directed energy to fuse or melt materials together. Material jetting and binder jetting are similar to a inkjet printer. So you're spraying a binder or spraying material that will glue together as you're building it up. Over on the left side here, we have what actually started 3D printing is a polymer that is photoreactive. So this liquid will become solid once exposed to light. Typically UV light is used, and there's a couple different variants of that. And the part that we're interested in is the FDM. Can anyone see my cursor when I'm moving it around?
Yes, I can see it.
Okay, good.
The words are small, but I can see it.
Yeah. So here is the father of 3D printing. He made the first SLA printer, and this is the printer itself and the actual object that he made. He did this by scanning a UV laser over a pool of polymer, and that polymer reacted to the UV and solidified layer by layer. Okay. As you see here, here's his good list of what 3D printing is currently used for. Aerospace is a biggie now. A lot of people have been seeing not only the Mars rover, but also SpaceX. And SpaceX has been using 3D printed parts, especially for their Raptor engines, quite exclusively. And they're able to make parts that have internal piping and capillaries that would be impossible to actually build out any other way. Archaeology, I know various archaeologists are scanning various artifacts and preserving them. Also allowing those artifacts, especially if they're single artifacts, to be brought to classrooms and or even tested and used for experimental purposes. Was that?
Can I add a quick story?
Yeah, go for it.
So it's been really advancements in archaeology. I have a friend who's an archaeologist, and some of the stuff they're doing is amazing. But they're also solving a lot of mysteries out there as well. In fact, they've had a couple of old molds that were so brittle they couldn't actually do anything with it, because if they did anything with it or try to use it, it would all of a sudden break apart. So what they did was they 3D scanned the molds, and then they made the molds, and then they reversed it out to make the model for the 3D printer, and then were able to print what was inside of it. And by doing so, they were able to figure out like where it was made, how it was like where it came from, and solve a couple of mysteries. They were also able to send it to many different museums and scientists, and you didn't have to worry about breaking things down or sending or shipping them the originals, because you can get almost exact printing with a 3D printer. So it's really kind of interesting, the kind of stuff that they do. And that's just kind of like regular archaeology. Then you have like paleontology and some other things like that, anthropology. And so it's being used in all sorts of different fields that you wouldn't really think about. But I thought it was pretty interesting that they're able to reproduce using the old original molds and have it pretty much exact. But go on.
Architecture. Oh, here we go. Oh, okay. This is background information in the chat. So architecture. There are already places that are building architecture that is 3D printed, usually out of concrete. But there are also bridges that have been fused, and they've been quite spectacular because effectively an armed robot welds small pieces, beads of material line by line, and it took a few months, but it built a complete walking bridge this way.
Do you have a picture of it, don't you? Can you show it?
Actually, maybe we can just go through here. This is a rocket engine. This is different materials here. The Archaeology, we have the scanning product. Of course, here's a scan of a dinosaur. I actually do quite a bit of this. Here is one of the bridges. Yep. It wasn't the bridge I was thinking of, but this is a very good example of one. And here is one of the houses that is built up layer by layer with concrete. This actually goes surprisingly fast and makes fairly complex buildings. There we go.
And one of the things we're able to do with architecture is, as you can see with this building, they're able to print on a curve. So curves are very difficult to be able to reproduce constantly using some
cheaply,
of the cheaply materials that they have available. They cost molds, and anytime you have to do a mold or something like that, it costs expensive. Anytime you have to have the prototype. So this way you're able to print it, and then you're done. Cost effective.
Yes, we have 3D printing of food. This is actually pretty wild. These are actually print on demand. All sorts of interesting things.
Yeah, and one of the cool things about the culinary arts is that you wouldn't expect it to be in, let's say, catering, but anything that you have to do kind of a rote action, like hundreds of times over and over again, it's great to be set up for like a printer or something that, mechanical that you can run through. So they have a couple of 3D printers going, and let's say they have like a pastry, a very delicate pastry. They can have the 3D printer kind of go out and actually make that pastry in the exact shape that they want to, and then before they cook it in the oven, and they don't have to sit there and do it. And it's exact every single time that they do it. So they're using that as effectiveness and as quite effective and used a lot more than you might think in the background.
And dentistry, the SLA printers, the resin printers, they use this quite substantially. In fact, most of the dentists that I have talked to own at least one of these printers. In the medical field, not only building replacement parts, because each of these have to be custom made, but a big push has been happening recently with makers all over the world printing out hands and other prosthetics for children and people that can't afford prosthetics. And the only thing you need to replace is you just keep all the screws, and they'll print you a new one when you grow. So for children, this is a wonder because they're able to have prosthetics that grow along with them.
Yeah.
And
I'm sorry. Go ahead, John.
Continue.
And I just want to add that we actually have a couple of links in the book to some projects, because there was a school out in the Midwest that took it as one of their community projects, is to basically use their 3D printers to actually print out for a group of people and then send them to them. Because what they did, all they need is kind of like a photo and sort of the size, and they were able to take with the photo and measurements the size of the actual prosthetic. And so they were able to do that. And what was really interesting about that article was that the middle class kind of did the 3D printing, but they helped the elementary students actually assemble them, putting like the screws and things together. So they brought most of the school together in order to make cans that they were giving out to people who needed them. So it was rather interesting.
And build on demand. This is a big area for 3D printing. Actually, this goes kind of also hand in hand with prototyping. It allows you to build something and make a one-off very quickly and very reliably when normally you would actually have to go through quite a extensive process to make that first prototype, or you would actually have to modify a non-custom part to fit a custom fit, like the horseshoes here. And before we continue on, I actually neglected to do this at the very beginning. If anyone's interested, I don't. Is everyone here new to 3D printing? Have they touched a 3D printer before? What are you looking forward to with the 3D printer that the regional center has purchased and has available? Just kind of curious.
Well, I'm new to it. I mean, we have one in our school. We have two actually, I think. And we have a makerspace that we're creating. So I wanted to learn how to use it so that we can help create a curriculum, you know, and help teach the kids. But the kids already are using it without, they just jump right in, and it's pretty exciting.
Of course. That's great. Thank you. Anyone else?
Yeah, so I just think that there's a lot of opportunities for teachers to try this. And Gary, that's great to see what you said in there. Because that's what we're thinking, is that teachers just need some opportunities to play with a 3D printer. Both of my children have 3D printed all kinds of things, but I have not really played with it myself.
Yeah, I'm looking to make 3D models of mathematical ideas for my classroom, like fractals and dimensional things.
Oh, that's very good. I actually have a picture of a model that fits into that category here. Have you actually? Oh, there you go. Okay.
Yeah.
Very good.
Mm-hmm.
Anyone else?
So Jacqueline just joined us. Jacqueline, have you had any chances to play with a 3D printer? She just joined us and I put her right on the spot.
I think she's froze.
Yeah, I think it's frozen, to be honest.
No, I haven't.
Oh, okay. There you go.
There you go. I can hear you now.
Sorry about that. We had a power outage here.
Yeah, it sounds like storms are rolling through. Yeah.
So no, I haven't had an opportunity to use a 3D printer in the past.
Okay.
I'm going to turn off my camera so I get better speed.
Sure.
Thanks.
All right. So is there anyone else that want to contribute? Okay. All right. Now we're back to that diagram again. I apologize if this is a bit small here. We'll go in more depth into this area presently.
And in the book, we have links to a lot of these images online, and we have larger things. So if there's anything that you can't read that's in the presentation, chances are that we either have it that's larger, or we have links to it where you can find them on the net.
Yeah, and definitely feel free to stop me at any point and ask a question. Okay, stereolithography. This was one of the very first methods of 3D printing, and it's quite interesting. You scan a laser beam, you pretty much trace out an outline of the object that you want in resin. That resin reacts, and once you're done a layer, the platform moves, and you rinse and repeat to another layer, and you continue that until you're complete the object. This is a very precise, very high resolution method. It can make parts that to the naked eye look like they've been blow molded, very smooth. And let's see here. So that's that version. Okay, this is the second version. This second version here is very similar. Use the same plastic resin, but it kind of does it invertly. It actually hangs the platform into the resin. It does it at the interface at the bottom. There is a piece of clear plastic at the very bottom, and either a light source is reflected up onto the resin, or you have a LCD screen, just like a normal computer screen, that acts as a mask for UV light. And this is very interesting because this is extremely fast, because it doesn't have to outline each layer. It does each layer as essentially a photograph. Also, these are now in the DIY market. You can actually buy a small MSLA for about $200, and they're pretty easy to use, though the build area is about the size of a large cell phone. So it's a small parts, very high resolution. Laser sintering. Another one with the laser, but rather than having the laser react with a photosensitive material, this is actually melting the material, whether it be glass, metal, particles of thermoplastic, anything that the laser can melt. Each layer, a new layer of material is dusted over and flattened, and that layer is effectively welded onto the previous layer, and then the platform moves again. And this is the one that most people are familiar with. I liken this one to, and actually you can actually buy these in the store. It's a hot glue gun on a plotter. You have an XY plotter with a hot glue gun. You have plastic material that you can melt, and you just follow an outline. And coupling that with a computer and stepper motors and a full gantry, it can repeat that very precisely over and over. But when it comes right down to it, it is a hot glue gun. You can actually buy handheld 3D printers, a 3D printing pen, they call them, and build your own freestyle 3D printers, 3D prints, which is kind of fun. So we're going to focus on the FDM and FFF type of printers here, because these are the ones you'll be working with. There are three major types. We have them outlined here, but they all incorporate is that? Yes, yes, yes. Let's see here. What was the name of that?
The Flash Forge.
Yes, the Flash Forge printer. Oh, I had the name of it right here. We actually get into it later.
The Glider 2, I think.
The Glider 2. That's what it is. Yes.
Yeah,
So
that's what I was looking at.
I actually put the picture of the model here in here later. So all of them effectively, you have a framework where you have X, Y, and Z motion and a printing head. How you get to that is done in 3 different ways. And here's a picture of 3 different types. This one has the one of the motions where the bed moves and the head moves up and down. This one that is reversed, the head stays in this plane and the platform moves up and down, and this is a completely different type. As you see, they can use different coordinate systems. If anyone wants more information on this, it's in the book and I can explain it a little bit more later. Usually this is kept from you with the software. I see someone laughing about that, but it is actually quite interesting. All right, and yes, the Flash Forward Glider 2. So yes, that wonderful hunk of wood on the left-hand side is my first 3D printer, all custom made, and it came as a kit from Makerbot, one of the first retail kits out there. This one on the left-hand side, you'll see these all over the place. This is essentially what's called an i3 configuration. A lot of cheap 3D printers, and some good ones too. But I mean, most of the cheaper ones will look like this because they're easy to manufacture, and there's very little to go wrong with these. Here is a modern Makerbot. Looks a little bit different. And here's one of the deltas with a completely different, rather than having a XY gantry, it's able to move the head side to side in this on the round platform by raising and lowering these arms. And here's the Flash Forge. This is a pretty nice printer, so you did get a quite nice printer. It has quite a few amenities in it, including Wi-Fi, a filament sensor, and auto leveling, which is nice. So let's go over to what actually goes into a 3D printer here. First, you have your filament. We're just going to go basically over this real quick. This is the thermoplastic in a spool. This is your extremely long piece of hot glue. The overall frame and gantry. Like I said, there's a couple different versions of this, but they basically work the same. They have stepper motors that will very precisely move these arms up and down, side to side, and in and out. You have your extruder, which actually pulls the filament into what's considered the hot end, which is the part that actually melts the filament, and there's a small nozzle at the end. And this moves back and forth onto the print bed, building your model. And this assembly right here is a fan to cool the filament back down. And of course, your controller and power supply. Am I going too fast, or is that good for people? Okay, we got at least one good. All right. Okay, so getting a little bit more into the nitty gritty, the filament comes in two different sizes. The original 3 millimeter size was prominent when 3D printers first came out. These spools are actually used in factories, and the factories would run these, cut off lengths of them, and melt them as needed. Having such a wide diameter filament meant that the extruders in these DIY printers couldn't be very precise. And as 3D DIY printers started becoming more popular, they made a smaller size, the 1.75 millimeter size, to allow these printers to be a lot more precise. So nowadays, most printers, except for the very large ones, will use 1.75. So if you're looking for buying filament, chances are it's going to be the 1.75 unless you have a specialty printer. Getting into the materials themselves, we are talking about thermoplastics, and each of these thermoplastics have different properties. And this is a quick overview of some of the properties that we'll be talking about here: how much they bend, how much they compress, how much they can be pulled apart, shear, or twisted. And these different properties may affect the filament that you want to use for different projects. Like a typical little statue that you would have, this might not come into it. But if you're making a part for a geared car, or a little motor or something like that that has moving parts, you might want something that has good toughness, maybe some good rigidity. If it's going to be something that you're going to attach and you don't want it to snap right away, you want to have it have some give, you might want to be able to have it stretch before it gives up and breaks. So this will come into the next section here. With 3D printing, this is a crazy matrix here. But and we can come back to this later. There's a lot of give and takes, and this is the part of learning the right materials, the right layer height, the right infill, the right quality that you want. There's a lot to juggle. There's a lot of variables, and little graphs like this can help. This is akin to photography, where you have to juggle exposure and the f-stop and the shutter speed. And you don't have to memorize this or anything like this, but this is something that will grow on, and having something like this might help. That if you increase the layer height, and it's going to decrease, or if you shrink the layer height from something that's very thick to something very thin, it will take you an inordinate amount of time longer. If you increase, so we'll get it farther into this. This will come up again, but I just want to let you know that the materials themselves have all their own abilities, and how you print them will change those properties. One of those is FDM printers have a grain. Since they're printed in layers, they have each of these layers are fused to the previous layer. So if you make a part, as you see here, if you put load on this upper part, chances are, just like a piece of wood, this will snap along the grain. Over here, this was printed in a different orientation. This was printed with the L on the build plate. If you put a load here, this is where you would get maximum strength. So this is another element that can be brought into teaching about the different properties of not only the materials, but also how these materials are put together and what orientations make more sense.
I think we lost you, John. Can we hear?
There's no sound, John.
Yeah, something happened. There's no sound.
Hello?
Yep, now we hear you.
All right. Well, that was really weird. All of a sudden I heard a beep and I was gone.
It wasn't me this time, swear.
Okay. Well, and it's still sunny out, so no thunderstorms yet. So there's multiple factors here, and each of these can be come into it's like when I was building a project, we had to make sure all the gears were flat to the build plate, because elsewhere the teeth would be breaking off all the time. So these are some considerations. And here is an overview of the different thermoplastics that we typically use. There are quite a bit more in this. There's an entire chapter on this in the book. Truth be told, most people don't use 80% of the types that are out there. ABS was the original type. This is what Legos are made from. It's very strong. It has good heat characteristics, and as you see this graph here, it shows all of its properties. PLA is currently the most popular plastic. It doesn't have very good heat qualities, but it's quite strong and it's very easy to print. There are types of flexible filament, which once printed end up being kind of rubbery. In fact, that octopus at the very beginning that was holding the pencil, that was made of the TPU, and that was it's fairly soft rubber feel to it. Then a close second is PETG. That has qualities between ABS and PLA. So, and then you have both HIPS. HIPS is like the material that many bottles, plastic bottles. There's a couple different variations of this, and then of course nylon. But when it comes right down to it, the ones that you'll be looking at the most often is PLA. Almost everything is done PLA. They have many different versions of PLA now. They have all the colors. They have PLA with different materials in them. ABS is rarely used anymore. Instead, PETG is used typically instead of ABS. And for specialty prints, you can do flexible or HIPS or nylon for parts. And these are ones that I went on to the website that are specific for your printer. I'm pretty sure you can actually use a third-party filament, but you would actually have to make sure some printers, they have specific spools which makes it a little bit harder to use third party. But they have, this is actually, again, PLA. This is, ABS. This is PLA with small bits of metal inside it, which will actually give these additional weight and some sheen. This has small particles in it that gives kind of like a marble look to it. Elastic, this wood filament actually has small particles of wood in it and is actually stainable. So this is quite fun. And this is, again, this is PLA, and actually this is PLA. So you'll get the most variety with PLA. Now, all of these plastics that you'll be using do give off, when they're being used, ultrafine particles and some volatiles. So having it in a large room, a ventilated room, is ideal. Another good point about PLA, because it's done at a lower temperature, it's the least offensive here. Was that okay, that's a person. So also, you'll want to keep all your filament in a container, especially materials like nylon will attract water, they'll swell, and then when you actually try to heat them, they'll create steam, and you'll have problems printing with them. So you want to keep them nice and dry. And this is actually a little printing booth that someone made here to allow you to print them without being exposed to air. It's an issue where if you took a spool of filament and left it out for a month, that spool of filament might not be good. It might get brittle, and it might not be no longer good to print with. So that might that's a consideration. Is there any questions from at this point? I know I'm kind of okay. I'm going quite quickly here. Definitely, if I'm going too fast or people have questions on this, do ask, because there's a lot of information I'm dumping here, and it just gets a little bit more denser until until we get into the classroom area. Okay, so we're back to the standard printer, and we have our filament that we've gone over. We have our build area, filaments, hot end. These are the linear rails. Here's a close-up of the hot end, well, the extruder, and then the hot end, and the cooling unit, the cooling ducts.
Let me just point out that these diagrams were taken from the book. So the numbers, if you look at the inside the book, will have the corresponding definition of what it is.
So this right here is the stepper motor. This is the tube that the filament would be coming into. This is a little release to allow you to load it. The cooling fan to keep this cold end cold, because the filament will readily melt, and this down here is typically around 200 degrees Celsius. So if that heat migrates up into here, you will get a jam. This is, oh, yes?
Does the melting point stay the same after your build?
It depends, like everything else. The melting point of the different materials vary pretty greatly. Mm-hmm. PLA typically bounces around 200 degrees to 230. Nylon could be almost 300. Okay. But PLA will soften at 150. I've actually had it soften at 100.
Right.
depending on it, but you can actually anneal PLA, and PLA will, it's sort of like annealing glass. You'll create a different
Molecular.
crystal structure,
Okay,
and that will boost its temperature a bit.
great.
So typical PLA, like the one that Aaron just showed, has a fairly midline. It bounces around that 200 mark. You can get PLA plus, which adds a good 30 degrees to that. ABS is 260, so it's kind of all over the place.
Okay,
But
that's something else to pay attention to then.
yes. If you put a PLA sculpture in your car, you might have a mess.
I might have a very interesting abstract piece of art when
Yes.
I'm done.
Well,
Thank
here's
you.
the thing. Some of them have
Yeah.
they have different glass points, and some of them will transition from being fairly rigid to fairly fluid in a very short range, and some of them have quite a long range. So some of them will just soften, and if you touch them, now you're going to deform them. But they'll
Okay.
keep their shape for quite a few degrees. If they're under load, then they'll definitely deform.
Okay.
So yes, typically we would go to like PETG if we're making parts that want to survive a little bit longer, and then nylon.
Great. Thank
Yep, no problem. There are multiple ways of getting the filament to the cold end. One is you just thread it into the gears of the cold end, and it directly deposits into the hot end. Some other printers, the actual cold end is quite a distance from the nozzle, and this is to save weight, because if this whole entire apparatus is moving back and forth and moving around and changing direction, you have momentum. So the larger and heavier that is, the harder that is to change direction. So to save some weight, that little stepper motor is usually pretty heavy. You put that at a different point, and then you feed it through a Bowden tube to the hot end. Both of these have their good and bad points. The one that you have, the glider, has a direct drive, so that would be the actual drive. They've made the entire head assembly small enough and light enough where they can handle it. And here's just a close-up. This is fairly typical of a hot end across most 3D printers. As you see, there's a little spring. This is a little tooth gear, and that just pinches and brings down the filament. This can be an issue with flexible filament. You would definitely want a direct drive for flexible filament, because it's hard to push a rubber band through a tube. So this actually pulls it rather than pushes it. This is the hot end. You have your heater cartridge, and then you have your thermistor, which controls the temperature of the hot end. So this needs to be controlled within a couple degrees. And this is your nozzle. This is the heating block to keep the heat, and to keep enough heat to continuously melt the material. Some faster printers can actually push materials faster than the heater can catch up. So these heater blocks can get quite massive to hold that heat. And then this is an interior where it shrinks down. The nozzle size for 3D printers is typically 0.4 millimeters. And typically these nozzles are of brass. But in the last couple years, this has, as enthusiasts do, sort of like computer enthusiasts, now there are hardened steel nozzles. There are nozzles that actually have a ruby at the very end that is hardened. So there's various materials, as you know, you can put through this, and the PLA that has the metal through it would wear down a brass nozzle in no time. So these hardened nozzles become a requirement. So if you have a material that isn't just plain thermoplastic and has something else in it, having a different material, having a different metal hot end and having a different metal for the nozzle specifically is kind of important, or you'll be swapping out those nozzles quite quickly. You can get smaller nozzles. I've printed successfully with 0.02 nozzles and all the way up to 0.8 to almost a millimeter. Are you talking to us, or I think you're on mute? Oh, okay. Never mind. And on the right here is a typical motherboard with like CPU power and stuff like that. This is less important. And some glory shots of your new printer here. As you see that this actually has a little bubble on top and the front area. ABS tends to change size when it cools. This can create stresses. So when you print with some of the materials, especially ABS, since you're printing it out in layers, you'll want to keep the entire chamber warm. If it's suddenly cooled, it will actually split along the layer lines. So your printer can handle ABS and just about any of the other materials. This is the printer head, and it seems like it's an all-in-one. So not too much DIYing and playing around with this one. This is part of the sensor that goes, that allows you to level the bed. It actually does have a fan and a filter to that filters out the VOCs and the particles, which is very nice. This is the hot end that's in that plastic container and the nozzle. And this is actually where the filament guide is. And one of the nice features with this printer is if you run out of filament, it will pull it through here. This is a switch. It will stop the print. It'll pause the print to allow you to actually load a new spool and start the print where it left off, which is amazing. Any questions from there? I went kind of fast. I hope that wasn't too much of an avalanche of information.
No, it's great info.
Okay.
We're
Okay.
going.
All right. So now we're getting into software, because all in all, this is a software run machine, and software comes into the process at a couple points. The original objects you'll be printing out will be models constructed by a variety of different pieces of software. Here's a quick list of very common ones. I know Tinkercad, Sculptress. Everyone has 3D Builder that has Windows. These are a bunch of programs that will allow you to either make parts using, some of these are CAD programs. Some of these are like Sculptress is a freehand sculpture program that allows you to make very organic shapes, people, animals, and there are programs here that do a little bit of both. Make Human is dedicated to making humanoid shapes. Yes, it's actually a kind of I think most of the ones here are free or have a free version. So I know Tinkercad might have a paid version, but the basic version is free.
Yeah, isn't there a pretty detailed list in the book?
Yes, yes, there is.
Yeah.
And there are also other programs like Blender, which is a program a little bit more geared toward CGI and making models for like videos and things like that. And that's completely free and has lent themselves a little bit more to 3D printing and editing objects for newbies. It does depend on what you're trying to make, because most of the CAD programs will allow you to make they're object-oriented, mathematical-oriented objects, allowing you to make gears, allowing you to make parts that you would normally put into a CNC. So if you're making parts for a small car, that would be that would work. And Tinkercad, LibreCAD are definitely some good ones.
So what if we?
Yes.
What if we have teachers that just say that they just want to try it and see what it does, and they just want to make something, anything?
So a program like Sculptress and ones of its type, like I said, this is an abbreviated list, are very freehand. And there are a couple programs, again, like Make Human, Clara. There are ones that are a little bit more geared toward, I have a blob in front of me and I'm going to use my mouse and pull out pieces of it. I have a piece of clay. And in fact, this is something I do daily is, I'm doing sculptures and we're doing human heads and human pieces. And sculpting as if you were doing clay in the computer is a big new thing, and a lot of like ZBrush is a paid one, but that's like professional level. Blender allows you to you can put squares in, you can put the squares together, make something, rhombuses, and you can take those, make more points, you can rip them apart, or very much like Sculptress or ZBrush, you can take those and kind of draw on them and build up materials. And so like you were sculpting, or you could take a part of it and bend it. So there's a lot of things you can do. And this is just software for creating objects.
Yeah, I was just going to say you could download stuff.
There is libraries upon libraries upon libraries. And in fact, they made search engines for these libraries, because there are now so many libraries of 3D printable parts from a big location that a lot of people go to is Thingiverse. And if you go there, they have anywhere from people making vases to replacement parts, like little gadgets, cell phone cases, you name it. Someone's made it on there. They have competitions where they'll give out. One of the competitions that I enjoyed was they had a sculpted tyrannosaur head, skeleton head, and then they're like, okay, everyone, make something out of this. So people would go and they made a door knocker out of it, or they made it into a dragon skull, or someone else made it into a pen holder, so so you could actually utilize these pre-made objects and bring them into one of these editing programs. You can start from scratch and make something your own. You can 3D scan something. There's multiple ways of doing that, anywhere from many photographs and uploading them to a site that will assemble those photographs into a 3D object, to dedicated 3D scanners. Then there's like more like it's wide open. Anything that you can make an object in, there's all sorts of stuff. So yes, there's Thingiverse. There you go. Beautiful. So yeah, there's just so many avenues to get resources from. It's absolutely wonderful. When we first started, you actually had to know how to use a CGI program, find a free one, and then make stuff for you to print there, because there was nothing else. Now there's almost too much. If you put in a search engine for just about anything, like a model for a cup holder, you will find hundreds of thousands of them.
Let me just point out too that they're not all the same level. So
Right.
when you're looking online, definitely do your research in terms of like reading the reviews, see how many people had it, because people do put up models, but they're all not made the same. Yeah.
Yes, so this is definitely a maker space too. So there'll be people there, including myself, that have uploaded all sorts of parts and artwork that I've done, and things that I'm sharing, to people that made their first object to print, and wants to share also. And people are usually very, very nice. They comment. They're like, oh, you had a problem here, you might want to fix this. Also people will make variations on a theme, which is wonderful, because like you would make let's say a part, like a part for like the Xbox controller, and someone's like, well, I like that, but I want a different picture on it, or I like that, but I want it for bigger hands, or so people would riff on that part that someone's made and make 20 different variants of it. So I heard another beep. Am I still transmitting?
You're good. We just had somebody leave.
Oh, okay.
I did ask you for 2 hours. A lot of people are used to 1 hour programs at this point.
Oh,
Okay, I'll keep it. No, I asked you for 2. So we're going to keep recording and hopefully they'll pick it back up and I'll send it out.
okay. So a quick outline of how do you find stuff. So like I said, you can make, scan, buy, or find online. The common formats are STL, which is the original format, which is crazy. 3MF is a new up and coming format. It is if you can find objects in 3MF, that is great because it contains a lot more information that's useful. And a CGI format called OBJ. That's a very common format that a lot of objects are stored in. After you find your object, you can load it into the next program, which is your slicer. We'll get it a little bit farther into that, but this program will translate that 3D object that you have made, scanned, or bought online, and turn that into a format that the machine can understand and build from layers. And from its name, what it ends up doing is you will have your object, and it, just like putting it on a slicer, it will just slice it into very thin cross sections, and then hand those cross sections to the printer one at a time. Once it's in the slicer, you get to do fun things like position it. In fact, what I'm going to do is switch over to oh, yes.
I have a question. When you're talking about scanning 3D objects,
Yes.
what's a common scanner that's used?
Oh, there are small 3D scanners that use a laser. A lot of people have made these DIY, and you can buy small ones. And they use how the laser curves over a surface, and it records that with like a webcam, and it's able to build up the on a turntable. The 3D object turns, and it's able to build up the 3-dimensional object from how that bright line bends and is captured. So it makes that out of like 100 different photographs as it goes around. There are other ones that run on various other aspects, very much like the Xbox Kinects, where it will use structured light. And very much like the laser, it knows what it's projecting, and the distortion of what it's projecting, it will reverse engineer into a 3D object. In fact, you can actually use a Kinect to actually make a 3D object scan yourself. It's scaled for human size, so anything smaller, it doesn't work very well. There's all sorts of little hacks you can do with that. There are also commercial ones that do that. In fact, I have one sitting right beside me that scans objects that are about a 1 foot cube. You can also use I'm not going to say it right. Photography. Wow, that's a tongue twister. All right. Photogrammic. Yes, it's in the book. Yeah. Oh, I feel so bad.
We go over in the book a little bit about scannings. I think we have a list.
Like I mentioned before, you take an object, you take 30 shots at this level, 30 shots at the next level, 30 shots at the next level, and you pretty much take every angle of this object with a known camera, with a known lens, feed all this information into a program, and it will chew on it and make a 3-dimensional object from it. It's a little bit finicky, but you can actually download programs or even demos of programs online to be able to do this. And if you're interested, someone write that down for a. I can give you a list of ones that you can download and play with. I do want to stress you need a powerful computer to do that with, and a decent camera. And then they have handheld scanners that the aerospace and industry uses to scan like cars, and a lot of them use it for inspection, for like mechanical devices and like rocket engines and aerospace. So these will real time, you just wave it at the object that you're scanning, and it will build up a three-dimensional object as you go. Those are thousands of dollars a piece, so they can get quite ridiculous. I just ended up pricing those out from $8,000 to $30,000 for one of those type of scanners. So there's a wide range. There are DIY versions that you can get that will scan small objects. So I hope that answered your question. That was kind of a long way around. It happens to be something that I'm doing daily at the moment. We have a couple different scanners, and I'm constantly scanning things, and we'll be actually going to a school in the next few days and scanning one of their mascots, which is a statue out in front. And then we're going to be shrinking this down to allow them to make a small version, and it will be identical. So, all right. And like I said, this is just a quick overview. We'll get into what supports are, or positioning. Like I said before, positioning the object is kind of important. If you want strength in one dimension, you need to position in a certain way. There are other things that will be coming up that you might need to move the position around and change its orientation. Supports are an artifact of 3D printing. I'll be getting into that shortly. And for the short version is, if you took your 3D if you took your nozzle and your hot glue gun and just kind of did this in midair, what you would do is get a stringy mess. And so you need to actually print it on something. Well, the problem was if you get up into the air and now you're printing something over here and there's no support for it. So what the 3D printers do is that they'll build their own supports out of that material. So there's something to print on. So it's a way to handle overhangs when you're building something. Now, the different processes use these differently. The ones that have liquid vats don't need to worry too much about that. And the sintering one, the actual material itself is its own support, because you have an entire box full of particleized material of that type. So it's like you would have an entire box of small particles of metal. Then you would set your print settings. You would set up your printer, clean it up, load the filament, print it out, monitor the printing, and then finally clean it. Just want to go over this real quick because we're going to be going into some of these parts, and I'll be getting a little bit farther into it. So this is the slicer that you'll be using right off the bat. It's called Flash Print. It comes with your printer, and it is a fairly basic one, but it also allows you to use all the features of your printer, and not drown you in all the advanced settings, because there are quite a lot of advanced settings. Another free slicer program called Cura actually has 3 modes, basic, kind of mid-level, and advanced. And the menu goes from 3 lines to about 20 to about 200 of different variables you can set. So when you get to the advanced level, there's a lot of things you can tweak, and there's a lot of features that you can play around with. This is a great program because it kind of hides them at the offset. And let me see if I can transfer you over to, there we are. Can everyone see that?
Mm-hmm.
All right, so we're now live in FlashPrint. This is one of my test models. It's the Mau Cow, because cats.
All right, so being stupid, where did you get that model from?
I made it myself.
And then imported it into this.
Yes. I made this myself in, I do believe, Blender.
In the models in the book too, so they can
Yes, it is. And I modeled it to show off a lot of the issues you can have 3D printing. Get a little off on a little side tangent here when we're talking about overhangs. This tail, there's nothing under it. So when the printer starts trying to print this, it's going to be printing in the air, and it would never print this tail because it would just become a mess right here. So your slicer will have to do something about that. And in fact, when you look under this, everything that's blue is on the build plate, build surface. Everything that's red is an overhang. So that gives you a nice visual cue of what things might need to be supported. So the end of this tail requires support. The mid part of the tail doesn't, because you can actually, one layer can go on the other layer, but they don't have to be completely on top of each other. They can be offset. So if they're only offset, you can make a 45-degree angle with absolutely no problems. Anything more than 45 degrees, then it starts getting a little bit more dicey. When you get to about 80 degrees, it has nothing. Okay. What books? Okay. And then as you see, rounded surfaces tend to need support because the curve here is below 45 degrees. The curve here is greater than 45 degrees. And same with this curve and some of these other areas here. I'll get into these internal spaces. So from here, we get to see the top view, left, right, bottom. This is a nice 3D space. You can move around in the 3D space. This volume is the volume of your printer. Anything that fits into this square, you can print. It's a good size printer. So that's quite nice. And I think this line indicates the front. You're able to move your part around. This program will automatically orient us onto the onto the build plate. And you can actually see the stats here, and you can force it on the platform, and you can force it to be centered. Rotate, let's say if I want to print this on the side, I can rotate it in any dimension or reset it back to where it was. And I can actually say, and I can also scale it up if I want to. So I can make it larger or smaller. Let's make it larger. Uniform or by a certain dimension. You can also cut an object. This is usually to break an object into two pieces because it's particularly hard to print, has too many overhangs, or there's not a good way of printing it. So you can cut it in half, put those two flat parts onto the build surface, and then glue them together later. Then when you're all done putting this on, now we can get into the support area and hit this wonderful button called Auto Supports. Oops. Let me change something real quick. It's doing the wrong type of support. There we go. There we are. So as you see, all these green lines are where it's building up material, which you can break off later, and will support your model. And as you see, that there's this line that I can put around, so I can put these supports in manually. And so auto support usually does a pretty good job, and then you can finish it out doing manually. This is a little bit of an art form, being you want supports, but you don't want too many supports. So if you go overboard on supports, that's just wasted material. So you'll find that happy medium where you're just like, oh, this is exactly what sort of supports I need for this material. Materials like PLA, like I said, is easy to print with. So potentially, it depends again on the material and some other factors. This can be a rough surface, so you're absolutely right. When I was printing out the 3/4 scale head, I had the head leaning backward about 30 degrees. So all of the face was facing upward about 30 degrees, so there would be no supports on it. So there was only a little bit of supports under the chin and a little bit of supports in the back of the head and in the neck cross section. The rest didn't need supports. I think there were some minor supports under the ears and maybe one under the nose. So orientation can allow you to minimize where the supports are and thus minimize any damage the supports would make. But yeah, some good old sandpaper does that wonder. And at the very end, I have I go into some quick cleanup and ways of getting rid of any issues, even using various putties to fill in cracks or rough areas if you're going to be painting them. This model is particularly made to be painful to print. So if you can print this model out very nicely, that means you're doing a good job. If there is a specific issue with this print, then it will show, it'll help you figure out what that issue is. Like this tail goes down to a very fine tip. Well, you have both supports here and the printer will be going over this area, it's very small area, over and over and over again. That cooling ring that's on the printer cools the filament as it's being deposited. If the printer goes back to that spot before that's fully cooled, then it's just going to start moving around that material, and that material will also be getting hotter and hotter and hotter, and you'll get kind of like a mushy mess. And there's like degrees all the way in there. If you cool it too much, it might become brittle and not adhere to the next level. So finding that happy medium is a thing. Typically the program takes care of that, but it's a place that you can play around with. So finding where how much cooling you use. PLA loves cooling, so it's a wonderful material to use.
So there is with this knockout, there is in the book a list of troubleshooting. So
Yes.
Seeing a problem, you can look in the troubleshooting area and you can see it kind of identify what the problem is.
And as you see here, I can actually change the overhang threshold, hit supports again, and as you see, I increased the limit so there's less supports. So with PLA, you might be able to get away with this. With ABS, probably not, because it would sag. So some fun things here, and then you would go and then go to the print menu. You'd pick which printer you need, what type of material, because it will handle some of the things like cooling, how fast it's pushing the filament through, and various other options through material types, whether or not you have supports enabled. A Raft will allow you. So what? Let's print a Raft. Yeah. So I just told it to do its thing, and it's now slicing it. All right. Now this is a fully sliced object. I made it large, so it estimates that this is going to take 4 hours to print. 4 hours and 17 minutes. It's going to use 14 meters of filament, which isn't actually a lot. And we can actually look through this and see all the layers. So this base part right here, which wasn't there before, this is called a raft. This allows you to build on plastic rather than the build plate. Old school 3D printers, getting that build plate perfectly level was super hard. So you almost always printed on a raft because you don't want that print head smashing into the build plate. And if it was just a little bit off, you would always smash into it on one side. With the modern printers, that's less of an issue. But you can always print with a raft. It uses up more material. Then, as you see, here's the outside. I wish it would actually do it in different colors, but that's the limitation of the slicer. This hexagon pattern is what's called infill. Rather than making a solid part out of plastic, there's really no need for that. It is taking that interior space and making a honeycomb, a nice strong honeycomb out of it. You can change what sort of infill there you want to use. And this also is an added benefit when you get to the top. As you see, it puts a roof on. This acts as support for the top of your object. So essentially it's built-in support. As you see, it's even building support in this hollow section of the cat because it needs to fill in this area right here. So this is endless fun of going through this. And as you can see, it built up the nice supports here. You have a nice base for the supports. And the printer would print this out just like that. Steph, real quick, the video, where did we put that?
Actually, it was right in the beginning,
Okay.
like slide 3.
All right. I just want to make sure where we were here. We were at slide 60. Yes, here it is. We'll have some fun time lapse. Can everyone see this all right? Now this head is actually moving all over the place. It's taking the picture when the head's in the middle. So this is actually jumping all over the place. It's taking one frame every layer. Should give you a good idea. I think that's for a Nerf. Good idea of what it should look like while you're printing and how it does layer by layer. So as we're seeing, this program also allows you to send your jobs wirelessly, allows you to monitor progress, and it allows you some manual control of the printer, so you can raise and lower the print bed and put in the filament, and because you need to actually heat up the hot end to put in the filament. And these right here are the more advanced controls. So you have layer height. Like I said, each layer has a specific height, and this height is usually much smaller than the width of the nozzle. So your vertical resolution is substantially better than your horizontal resolution. So if you want detail, put it in the vertical. This is set at 0.18. Typically, people 0.2 is normal, 0.3 is considered fast, and 0.1 is usually the maximum for these type of printers. 0.2 is about the thickness of a piece of paper. And as you see, the first layer height is a little bit expanded. This allows you to have some error wiggle room for that the print bed. Shells is pretty much how many walls, because each time it goes around, it's making a line, and that line is going to be just over 0.4 millimeters. And so is that wall 0.4 millimeters, 0.8 millimeters? You know, it's going to be a multiple of 0.4. So typically people print with 2 walls. If you want a strong part, I would go to 3 or possibly 4. And then the top layers and the bottom layers is how many layers will make your top and bottom. But that is counted in multiples of your layer height, not the dimension of your nozzle. Fill density is how dense that hexagon grid is, and this is at 15%, and the fill pattern is hexagon. You can do rectilinear. You can do usually a whole bunch of different things. People go crazy on this, but keeping it simple is usually the best, because the infill is mainly just support for the top layers. Print speed is dependent on your printer. My printer, my custom printer that I built, prints at about twice this speed. But this is a pretty standard speed for a normal printer. That's how fast the actual print head moves. And you see there's a difference between when it's actually moving and extruding material and when it's just traveling from point A to point B. The temperature of the extruder, this of course will change with the material, and the temperature of the platform. Now, some of these materials require the platform to be of a temperature so it will stick to it, and also so it won't cool too fast and shrink too fast and then pop off. So the platform itself is heated up. Materials like ABS require this to be about 100 C. PLA can be actually anywhere from 0 to about 60. Typically you want it, somewhere in between. That just makes it stick to the platform nicely. You definitely want it to stick to the platform nicely. If this thing pops off during print, it's bad. Of course, you're now printing in the air, and your piece is now sitting in the corner, or worse, the print head smashes into this every time it goes around and damages your printer. So it's very important to have your piece stick nicely to the platform. And then of course your fan controls. And then let's look closer to what it's actually doing. Well, here's the nozzle. It's the nozzle diameter, and this is the bead of filament that it is actually putting down. As you see, the bead is larger than the nozzle size. So typically when you're printing, I have a visitor here. Yes, I know. Typically, when you're printing with a 0.4 nozzle, the bead of filament that's going down is at 0.48. So that's good to keep in mind. It's not 1-to-1. It's always a little bit larger. And the reason for that is that you want a little bit of squish to that bead. On the right-hand side here, the top one is a perfect bead, and you're giving a nice consistent bead of filament. And because it's putting it on the previous layer or the print bed, and the nozzle is scraping across, you'll get a nice flat top and bottom. If it's too high, you won't have much surface area attaching to the previous layer or the print bed, and it will come out like a tube of toothpaste, and it may stick, it may not, you're not smearing the top either, so that top part is, you're just essentially putting down a cylinder. If it's too low, your extruder will struggle to push out the material, and anything that it does struggle to push out will be spotty and smeared all over the place. This is also a danger of knocking the print off, because your head would crash into the print or dig into the build plate. So I should have switched out here. So material not sticking, too squished, perfect, about 20% larger. And here's a physical picture of how it goes wrong. This is a perfect first layer. You can see the individual lines. These are the shells. This is the infill of the first layer, and this is it struggling to push out that first layer, and it's having issues. Layer heights. On the far right hand side, we have, let's say, a layer height of 0.3. As you see, as you go around a curve, that layer height, when you start going around that curve, you start getting stair stepping. Decrease the layer height by a notch, 0.2, and that stair stepping becomes reduced. And once again, at 0.1, that's reduced even farther. So here is a closer look at that from a side view. So that resolution of your layer height will affect curves and angled prints. And here is a physical shot of a print. As you see, going from the coarse 0.3 layer, these are all done with the same nozzle too, down to 0.2, down to 0.1. Other interesting part about this is that the 0.1 takes twice as long as this 0.2 to print. So when you start jumping these steps, the time it takes to print these out increases dramatically. So remember those matrices that I showed first. Print quality, print time can conflict a bit. Here is at an angle, and you can see the stair stepping. Same angle, different layer height. And here we go again, different angles. And you see I did it more of a topographic look. You can actually see low res, high res. And if we want that not to be stair stepped, well, we change its orientation, print it vertical. Here's a quick overview of infill types. You say rectilinear, honeycomb, all these different infill types. You get to pick which one you want to use. The denser they are, the more they support the top, but the more material that they take, the less dense, the less they're going to support the top, and you might get the top sagging in a little bit. So if you get any little, the top pillowing in a little bit, that means your infill isn't dense enough. And here's some variants. And here is actually some 3D infills, which are actually quite amazing. These are actually three-dimensional structures built in as the infill. This is very fast, so it just does a wavy line, but it varies that wavy line over time. So both of these infills, these are kind of newer ones, make the not only support the top, but they also add some structure. Yeah. And now we're to supports. Like I said previously, no supports are required. Anything less than 45 degrees. 45 degrees is perfect. Anything greater than 45 degrees, you start getting into the danger zone. I've been able to print close to 70 without any issues with a strong fan. So there's definitely tweaking room. As you see on the bottom here, this is what happens when you don't use supports. You get a tangled mess. So you definitely require supports. Also, as you see, the farther the support goes out, the larger the tangled mess. Here's something real quick, and this is something that's fun to teach with the kids. I actually have this in the book, an entire alphabet. The Y has 45-degree angles sides, doesn't need supports. The H is a special case. The H has a span that would normally require supports. But if that span is small enough, it actually has support on either side. So depending on your printer and depending on your cooling, you can actually print a piece of filament that would span that area with either minimum or no sagging. The larger it gets, the more chances of it. But if it's of a modest size, typically anywhere from a centimeter to about 3, you can get away with it. So you can print small bridges with no problems and no supports. Large bridges will tend to sag and require supports. And then the T, it's only supported on one side, so require supports. Any questions on that? Because this is a kind of a fundamental that some people have a problem with. I think this really helps visualize it. And as you see, what happens when this is a bird nest. This is what happens when your print breaks or gets knocked off. You end up with a pile of junk. And this is what happens when you don't have supports versus supports. And there's different ways of supporting something. Like I can put this block down, and if I support it on these two sides, I would have a lot of scarring. I might have scarring on these two sides. Or I can do it like this. So I only have scarring on one side. Or I can print it flat on the build plate and have potentially no need for supports for a cube. Something a little bit more complicated would be the shell. And printing the shell on the side, you would have supports all the way down the side of this. Since I'm printing this vertically, I only have a small amount of supports. But run the risk of this thing snapping off and being ruined. So there's a lot of wiggle room and a lot of experimentation. And this is where I have a lot of fun. Quick Q&A. I know I've been calling this periodically. Do anyone need a minor break or anything?
Well, actually,
oh, we're almost to the end.
Yeah, I was just going to say, what you might want to do is ask them if they have any ideas of questions about the future. I know if you go to the other slide, you have projects and different things.
Yeah. So if no one has any problems, I'll just lunge into the next section. Cool. All right. In the classroom, potential uses and projects. Of course, there's material that you're going to be using. It costs money. PLA is pretty cheap. You can make quite a bit out of one spool. Are you making a prototype? Are you printing something that a lot of people have already printed? How many prints are going to be made? Remember, these prints take time to print. What are they going to be used for? Because what you use to print them with and how you print them dictate how they're going to be used or what effects are going to be used. So again, gears or mechanical items are very important here. Let's see here. Does it need a specific level of strength? How many walls you want? Specific materials? And what's the time frame? And of course, in the classroom, here's an example of one of the little programs. This is on an iPad. This is a program that makes fun little creatures that you're able to make, and they can save those off and send them to a computer so you can slice them. There's a bunch of these. Here's someone making, here's a classroom, and here is someone making their own chess set, and so on. Now we have uses in the classroom is all over the place. It's a wonderful thing because you're of course creatively thinking, you're engaging the students. You can make items that they can learn with. They can learn while making the items. Just the process of learning how to 3D print and a lot of the stuff that I've already gone over is an interesting and useful thing to learn in itself, let alone concepts like material properties and physical properties.
A couple of chapters in the book that kind of cover over a little bit more in depth and give examples and give some ideas as well. I think in the beginning of the book, like chapter 3, and then later on in the book, we'll have examples and some links.
Yeah, job ready skills. I know a lot of people that it's now becoming my full-time job. It's a lot of people's part-time job where they're printing out items constantly for people, for themselves. There's entire networks out there that you can say, hey, can someone print this out for me? And there's entire maker groups that will print that out for you. And tangible objects and everything. So a wide range of areas of learning across the board. Pretty much anything goes here. I know that we're getting down to the end here, so I'm going a little bit faster. Here's a couple quick projects. This quick project, top of the spray can broke. This is no longer functional. That's what I'm working with. I only have this nozzle. This would be the replacement, but the replacement has the wrong size hole. Bring it into a CAD program, make a simple shape, make the right size holes, print it out, and now I have my object, my functioning adapter. This is actually something I did. This was I needed the adapter, so I sat down and made this in maybe a half hour. Here is a friend of mine that this object right here, you would actually have a clip on the bottom here that would hold a cell phone. And this goes into the guideline of a tent. This is to hold your cell phone so you can watch it while you're sitting in your tent, typically for biking, because it's small, narrow tents. This is him prototyping it. I actually built it for him in a CAD program. This is one of the early prototypes that we printed. This is his first lots that he did. And his current thing is he was able to make enough and make enough money off of these that he was actually able to make a mold, which are very expensive. You can't prototype with molds, and that's his business. This is that 3D scanner that I was talking about. This is a very expensive sneaker that I was commissioned to scan. I think this sneaker is $4,000. I don't know how a sneaker can get $4,000, but it is. This is my 3D print of said sneaker. I believe it was 1-to-1. This is this sneaker being set up for a mold and a pour to be turned into bronze. I tried to get the final picture of this. This is an ongoing project, so maybe later I can send what this finally looks like all shined up. But this is a project going from a sculpt in, someone recognizes. This is something that my wife sculpted in clay, was 3D scanned. This is actually in Blender, printed out, and then, yes, made into bronze. It's currently being patinaed, and we should be getting that later in the week. Electronics. This is a ring that was made for these LED arrays for some goggles. Exactly. This is actually the internal part of a piston engine. I've seen people that have printed out the entire thing and with a hand crank, and it was fully functional. Here's a pangolin, and it is this is printed in place, so all the joints work as you take it off the print bed. So you can do some pretty interesting printing on that. Here's a piece for a rail system. This is mechanical, and this is also very, very strong. Another device, this is, you put a piece of wood in here and this will move that wood back and forth. This is a dice rolling thing for games. So all across the board, GoPro holder, parts holder box. Here's that shell again from the 3D printed. This is the 3D printed. This is the real shell. Skulls, the octopus, props, more props, electronics, all sorts of stuff. Electronic box. This has saved me so much money by buying enclosures for electronics. This is actually flexible also. This is a for your wrist, mechanical, and even a phone holder. And here's another wonderful print out. Yeah. Quickly, the maintenance. I know this was asked earlier. Knife, razors, needle files, cutters, dental picks, deburring tool is one of my favorite because it's made specifically for this. Needle nose pliers and sandpaper. It's used to get off all the little nibs, to remove the supports, remove anything that the cleanup rough areas that supports were at. You can also use modeling putty, repair putty. There's gray filler primer spray you can buy in a can, and triple thick glaze spray. Both these sprays you would spray onto a model and will give that first layer. That first layer, it will fill in the layer lines and also fill in any cracks or bumps. And then you go back and sand that. With the triple thick glaze, you don't necessarily need to because it tends to self-level, but the gray primer spray is beautiful for that. And the putties are great for if you have a crack or if you're gluing two parts together. And then here's an example of, here's the shell with that first spray filler, now sanded, primer, the color layer painted on, and then with the final glaze. So printing it out doesn't have to stop after you're done printing. You can go into quite a few different levels of post-processing and cleaning up and artwork after you're done printing. And here's a little frog. He is made of wood filament and he is stained. I couldn't put I also printed out a baby Groot, but I couldn't put him in because of, well, yes. And in fact, I have an SLA printer myself, and I also print miniatures, and painting those are quite fun and difficult at the same time. And actually in the background, this is actually a prop made by one of the people in the book that we highlight in the book. So I do believe I've made it to the end. Pretty close to the time. Sorry about rushing that last part. This, as you notice, it's taken me 2 hours to rush through this, and this is a primer. There is a lot to go in on, and there is a lot in the book that goes into like the maintenance of your printer, calibrating your prints, calibrating the temperatures and the different materials you're using, because they'll give you ballparks. Like I have this PLA and they give you a range of temperatures. Well, what part of that range are you going to use? Well, you print out a couple test pieces and you figure it out. Then you write all that down, and then you build up a library of which materials require what temperatures, how they react to different things, and building up that library is as important as is a very important element of learning how to 3D print. And they're always coming out with new filaments, so you're constantly adding more to it. One of the things I do is print out these little test rectangles and write down on Sharpie what some of the stats were for that print. And they have a small like hole in it, so I put them on a keychain. So I'm like, okay, which color swatch do I have? Well, it's which material swatch do I want? So it's pretty handy. Yeah, so I think I'm done. If anyone has any questions and want to go into anything else, I'm free. Otherwise, you can always send me questions. I can answer those. Oh, the title of the book? Steph?
So the title of the book is the 3D print, and we will be having a couple of copies here. Send them to you.
That's embarrassing. There it is, right there.
Next one down. Go one down, John. Or a couple down. Yeah, no more. There, right up there, right there.
Okay.
Yeah, I think we 6 copies or something like that's coming. You should have them by tomorrow or today or tomorrow.
Yeah.
Now the thing with the book is not only does it go through hopefully progressions, kind of like what we did here, but like it goes into depth. But also there's a DVD, and if you don't have a DVD player, we can get you the files, or you can download them from online. But basically they get like test projects. There's different things more information. There's links for more information. So there's a lot of resources that's on the DVD or interactive as well.
All the models that I highlight are in there. There's a bunch of models like the alphabet.
A couple of challenge projects too.
A couple of challenge projects. And yeah, there's a bunch more additional stuff in there that's quite useful. I think the alphabet project is quite fun.
Yeah, that and okay, because where I think you touched upon earlier is a lot of times people skip the calibration part, and that's a really important part. And it's kind of like you got to do like the groundwork, or you got to do the pre-press, so to speak, before you can actually go and actually do the print. And so you got to make sure that that's all set, and so you're not, you don't hurt your printer or you don't waste material.
The wonderful part is that you actually did get a very nice, rather high mid-range printer that has a lot of features, and some of those features will actually make your life a lot easier. And one of the issues is that when this started with DIY, people were buying bare bone, either making their own, using kits, or using real bare bones printers, and also trying to learn how to use them. And configuring them and calibrating them was a huge part. And people would just abandon 3D printing because they couldn't get a good printout from them. And the nice part is that this has come to a point where you have to worry about the printer a little bit less. You still have to be nice to your printer. You still have to clean it. You still have to lubricate it. You still have to use your different materials and find the optimum settings, but it isn't as bad as it used to be. But so that's gonna help a lot of people. But at the other end of the spectrum, especially geeks like me, I like all that part. So that's why I'm able to optimize and build my own printer, and also have my printer running at high speeds at extremely high qualities. So you have a very good start here. You'll be able to print stuff fairly easily and then refine those in the future.
Thank you so much, guys. Much appreciated. And we do have this recorded, and we hope we'll get more teachers involved. And we'll have office hours during the summer, and you can always call me and make an appointment. And to me, the whole idea was to give it a try, just experiment.
Oh,
Yeah.
yes, definitely. And it's great because I love when people start playing around with this. It's hard to kick them off sometimes. So
That'll be nice. Thank you so much.
all right, thank you. Nice meeting all of you.
Thanks again. Bye.
Bye-bye.
Bye.